So, in our previous class, we were discussing about mass action law and how to identify number of electrons and number of holes in an not intrinsic, extrinsic semiconductor, p-type material, n-type material, etc. So yesterday I have discussed all these stuff for you, and in our previous class I have discussed about something called a depletion region, and I have discussed what is happening in the formation of the depletion region. I just want to brush up you again. In the course of formation of the depletion region, you will notice a diffusion current from P region to N region, and similarly, in fact, holes from P region to N region, electrons from N region to P region, and net current is due to the majority in that instant. But on the other hand, you will find minority flow also, like N region to P region electrons, P region, N region to P region holes, P region to N region electrons, which is in fact exactly opposite to the diffusion current. After some time, what will happen is the depletion region completely forms, and a potential barrier is set, and net current thereafter is zero. At that instant, drift and diffusion current almost becomes equal. The space charge region is purely immobile, right? Now, I told you yesterday about the same thing, and graphs also important as per my knowledge. See how charge density varies. I have shown you graph. Similarly, how electric field varies. I have shown you a graph. No, and how the barrier potential sets. That also I have shown you graph. Someone have an idea what would be the idea of the width of the depletion region? The idea of the width of the depletion region is of the order of few micrometers. And in fact, you increase doping, the width of the depletion region increases. Oh, no, 1 minute. I'm sorry. I need to correct. If it is a heavy doping, the width of the depletion region decreases. As you increase the temperature, width of the depletion region also increases. Remember, this junction, even though have some resistance, but it won't behave as a ohmic resistor. Its VI graph is not a straight line passing through origin when you plot a graph against voltage and current. Already in my last class itself, I have given you a clarity. If it is a germanium, the height of the barrier is 0.3 volts. If it is a silicon, the height of the barrier is of the order of 0.7 volts. This is all which I have covered in my last class. In the absence of external biasing, drift current is the same as diffusion current. Drift current is the same as diffusion current. Right. Yesterday also I have done. If we are plotting a graph taking, if we are observing a forward bias condition, the p-type material is connected towards the positive terminal of the battery. The n-type is connected to the negative terminal of the battery. See, remember, p side must be a high side when compared to n side, right? So, what will happen here in this case is, if ever you notice, in case of a diode, P side is higher than the N side, you can say confidently that the diode is forward bias. The reverse case is reverse bias. In the forward bias condition, what will happen is the potential barrier decreases, and junction width also decreases. Zero, it, it won't be zero. And so majority carriers will be allowed to follow the flow through the junction, and the current majorly is due to majority charge carriers. And this is of the order of milliamps. Okay. And the current is forward biased current. In the reverse bias condition, I told you very clearly, we will apply reverse to what we have applied earlier. P-type, we will connect it to the negative of the battery. N-type, we will connect it to the positive of the battery. And what you will notice is, in this case, the width of the depletion region increases. Okay, strength also increases. So therefore, only minority, due to drift only you will have current. So due to drift only you will have current. So only minority charge carriers will be drifted, and hence the current is due to the minority charge carriers, and since it is small, it is of the order of microamps, right? Now, small observations, I'll try to compare both small observation. So you have a forward biased condition here, and you have a reverse biased condition here. In a forward biased condition, P-type material is connected to positive, N-type material is connected to negative. Whereas in reverse biased, P-type is connected to negative, N-type is connected to positive. Right. What happens? Potential barrier reduces. Here in reverse bias, the potential barrier increases. Width of the depletion region decreases. See, width of the depletion region decreases due to two reasons. One, if it is heavily doping, also width decreases. Two, if it is a reverse biased, width increases. In forward bias, depletion region width decreases. Next, in forward bias mode, almost low resistance, zero resistance we will consider ideally. Whereas very high resistance in case of reverse bias, ideally we will take it as zero. Sir, zero, no, infinite. Infinite resistance in the reverse bias mode. So if you plot the voltage as a function of a current graph, you will see that the graph follows something like this. Whereas in reverse bias mode, the current and voltage characteristics are like this. I told you in my previous class, this particular voltage is called a breakdown voltage. And after this, current is literally independent of voltage. You increase whatever, nothing happens to drop, but current keeps on increasing. See, this new voltage part is nearly that is almost close to the barrier voltage. 0.3 volts in case of germanium, 0.7 volts in case of silicon. And the breakdown voltage is nearly 25 volts in case of germanium and 35 volts in case of silicon. I'm just giving you a rough idea. Right. See, what is happening specifically for a PN junction diode under reverse biased mode? Right. So what happens? Let me just in detail give you some explanation. Generally, for diodes, we won't speak anything about resistance because it's not a ohmic conductor. Rather, we will speak something about dynamic resistance. We will speak something about dynamic resistance. So, see, that part I missed here. I just want to update you that here. Anytime if someone asks you, forward resistance, forward bias resistance, simply do delta V by delta I. This is how you will operate in semiconductors, not V by I. Even see, usually this is how you will operate. Usually forward bias. Even reverse bias also you will resistance. You will operate almost the same. So ideally zero. Ideally infinite, like an open switch. But generally, forward by reverse ratio will be of the order of, in general, forward resistance by reverse biased resistance is of the order of 10 power minus 6. Just for your idea. Forward resistance by reverse resistance is of the order of ఎప్పుడు 10 power minus 6 అని కాదు. I just want to give you a range. 10 power minus 6 range. Ideally. I said ideally infinite. Ideally 0. In that case, 0 by infinite not definable. Next. I want to add something more to PN junction diode observations. Please, what is the difference between the previous class and this class? I have arranged all that content which was taught to your seniors, and I will use that notes. That reduces the time of noting, that increases the scope of explanation. PN junction diode, one using under reverse biased mode. What is your first observation? Tell me. First observation is that this is how you will show the diode. And this is a low voltage and this is high voltage. This is the identity of reverse biased condition. If the reverse biased voltage is made too high, what happens? The current through the PN junction increases rapidly. Remember, try to remember the graph. This is how you will find the graph. Okay. So this particular voltage is what you called it as breakdown voltage. Right. So what happens here is current increases very rapidly. Usually the voltage at this, the voltage when this happens is what we will call as a breakdown voltage or GNR voltage. So the breakdown region operation is actually classified into two categories. Or I can say the breakdowns are basically of two types. One is avalanche breakdown and the other is GNR breakdown. There are huge differences between these two breakdowns. Practically, GNR breakdown is useful in our practical applications. Avalanche means which is not in our control. A high reverse voltage, okay, you are applying a high reverse voltage leads to a strong depletion region, strong electric field near the depletion region. What will happen is this strong electric field, in fact, in some books, I have noticed it, tears off. They have used a word called tears off the covalent bond near the depletion region. And this tearing off results sudden formation of electron hole combination. For example, in this depletion region, suddenly if an electron hole pair is created, this is the direction of the electric field, you know this. So what will happen? A hole in this region is drifted towards P side. An electron is drifted towards N side because of this strong electric field. Yes, you can question me. Adepudu. That is called diffusion. This is reverse bias mode. What happens now? Huh? A drift direction cheppu. What is a drift direction? Drift direction is like this. In case of drift, holes move from N region to P region. Electrons move from P region to N region. Yes, what I told just now. In reverse bias mode, what is actually the current due to? The current is due to minority charge carriers. The current is due to minority charge carriers. Yes, that is the reason why it is very small. It is of the order of microamps. So, because of this, what will happen is, since they tear off the bonds, and all of a sudden they cross with the greater case, in the course of their motion, they will ignite some more collisions, and that collisions leads to breaking of more covalent bonds, and breaking of more covalent bonds results in formation of more electrons and holes, and this leads to huge current. This will leads to huge current. So that is the reason why all of a sudden you will find more current in case of PN junction working under reversed bias mode, and this is like an avalanche in snow mountains. Whereas Zener breakdown is slightly different. Same reverse bias condition, you are operating the same reverse bias condition, and the difference between a normal diode and a Zener diode is a Zener diode is a heavily doped PN junction diode. Since it is heavily doped, it will have a very thin depletion region. And this will have, because that the depletion region is thin, right, very sharp breakdown voltage. Because of this sharp breakdown voltage, before they collide another covalent bond, they will cross off the depletion region. So that avalanche condition is avoided in Zener diode. Normal diode and Zener diode, two differences. Normal diode, normal doping. Zener diode, heavily doping. Normal diode with under reverse bias, width of the depletion region is high. Zener diode, width of the depletion region is narrow relative to normal diode. Right. So depletion region is strong, so sharp breakdown voltage. That is the reason why Zener diode is differently shown, like a Z term. You can see a sharp breakdown voltage. That is the reason why the Zener diode is used as a voltage regulator, which controls voltage. Okay, now I just want to show you a simple circuit with Zener diode. Simple circuit with Zener diode. This is some varying input source, series resistance, Zener diode, and a resistor. For example, for our purpose, we are taking some 6 volts. Now, for example, I'll just give you a clarity. This is an input source that will change according to given conditions. You are using C. Z is represented there, don't forget. For example, I am operating this from 10 volts to 20 volt. The resistance of this part is, say, 5 ohm, and the load resistance is, say, 5 ohm, and the Zener breakdown voltage is 6 volts, for example. This is the circuit. Now see, try to please understand, when I am applying 10 volts, for example, when I am applying 10 volts, now this circuit, this case, suppose I am applying 10 volts. Then diode is of no use. Why, I will explain. Remove the diode part. Hold on. You will have 5 volts drop here. You will have 5 volts drop here. So nothing happens. Means the diode is purely off state. In this case, diode is in off state. Kusa. Diode is in off state. Why? When will it come into picture? The voltage across the load crosses 6 volts. If it is 10 volts, I have answered like this. Range, you can operate fluctuations 10 to 20 volts దాకా రావచ్చు సోర్స్. 10 to 20 11 to 20 కూడా వస్తుందిరా. 10 కి చెప్పారా, నన్ను చెప్పనివ్వరా. నెక్స్ట్ రైట్. ఫర్ ఎగ్జాంపుల్ if it becomes all of a sudden 12.1 volt, what happens? Definitely across load it will be more than 6 volts, but across a load, the voltage drop is చెప్పండి 6 volts only, because now diode is on. So what happens to the voltage distribution? Now what happens is the drop here will be 6.1 volt, and the drop here always maintained 6 volts. Okay, sir, what if it is 13 volts? What if it is 13 volts or more than 13 volts? Now, in this case, remember, suppose if it is 13 volts, it will become 7 volt here, because always across the load, the voltage now becomes 6 volt. What did you notice? Once you cross 12, thereafter across the load, the drop is always maintained 6 volts. This is called regulation, voltage regulation.
ఫిక్స్డ్ వోల్టేజ్ నుంచి జీరో డయోడ్ బ్రేకింగ్ వోల్టేజ్ పవర్ ఆఫ్ జీరో డయోడ్
Current into voltage of the Zener diode. Hold on, అది ఇక్కడే చేసేద్దాం. అది ఇప్పుడు ఇది 7 volts, 5 ohms. Now please tell me what is the main current. The main current is 7 by 5, 1.4 ampere. What is the current through the load? The current load through the load is 6 by 5, 1.2 ampere. So what is the current through the Zener diode? Remember, Zener diode is always connected in reverse biased mode. Now tell me, what is the current through the Zener diode? Tell me. The current through the Zener diode is 0.2 amperes. Anything extra will pass through the diode. And the current through the load is always maintained constant.
ఫిక్స్డ్ వోల్టేజ్ తీసుకుంటే
ఏ ఫిక్స్డ్ వోల్టేజ్? అదేనమ్మా, ఇప్పుడు ఫిక్స్డ్ వోల్టేజ్ 10 volts ఇస్తే పవర్ త్రూ జీనర్ డయోడ్ 0. ఫిక్స్డ్ వోల్టేజ్ 13 volts ఇస్తే, this is how you should check. First, what you need to check is, in the absence of the diode, try to distribute potential drop across the load and the input series resistance. Suppose across the load, if the drop is more than Zener voltage, then you come back to the question, correct the voltage drops. Now that's what I have done here. That's what I have done here. Actually, if it is not the diode, I would have written 6.05 volts, 6.05 volts here. I would have marked here 6.5 volts, 6.5 volts. Right. I didn't do that. Why? 6.05, 6.05, I didn't do that. Why? Across the load, you cannot apply a voltage more than 6 volts. Why? Diode will come into the picture. No. The action of the diode is responsible for maintaining constant potential difference. Don't forget, this is the reason. This is the reason. You cannot apply anything beyond this. That is the reason. Now tell me, on gene or diode, have you understood the fundamentals properly? Boys and girls? Right. So now, I'll do this part a bit later, because this requires some mathematical grounds. I'll just complete this theory. Test on that. Right. See, optoelectronic junction devices, purely semiconductor devices. The same PN junction diode we will operate it in different ways, and one such area is optoelectronic devices. And all these are related to interreaction of the diode with light. Relation. First thing, photodiode, light emitting diode. Well, we are all aware of LEDs now. Photovoltaic devices, solar cells. Practically, more or less, we are using this. Photodiode objective is for detecting optical signals. LEDs, source of light, like your earlier days bulb. Photovoltaic cells will convert light energy to electrical energy. We will discuss one by one. Photodiode. It is basically a PN junction diode, and it is fabricated in a transparent window. Why? It is supposed to expose it to light. Remember, you are exposing light not to the entire diode. In fact, you are exposing the light to the depletion region. The objective is exposing the light to the depletion region. Any doubt till this point? Now what happens? Remember one point. Photodiode is operated always in reverse biased mode. Theory type questions, you are expecting this. Reverse biased mode. Why and how and what happens? Under normal conditions, when you expose this depletion, otherwise, if I am not exposing this depletion region to light, under reverse biased condition, I will notice some current. I will notice some current. Okay, right. Now I am exposing light to this. Can you please tell me what will happen? Now you know clearly you will have conduction band, you will have valency band like this. Because of that, the light is absorbed by some electrons in the valency band. They will jump into conduction band, leaving a hole. As I am exposing light to this region, what is happening is suddenly electron hole pairs will be created. Are you following what I'm saying? You expose the light, That doesn't mean earlier it is not happening. Normally, intrinsically, at every instant, every corner, every portion, somewhere are there. Electron hole pair creation, electron hole recombination keeps on happening. We require both. Now, what is happening now? As you are exposing light, particularly in the region of depletion region, what is happening? Additionally, because of absorbing these photons. Now, can you please help me? What energy of photons is required? You can say energy gap. This gap is called energy gap. So, photons whose energy is slightly greater than Eg is just sufficient. Photon ni expose చేస్తున్నాం. ఏది ఎనర్జీతో బయటకు వస్తుంది? దట్ ఈస్ ఫోటో ఎలక్ట్రిక్ ఎఫెక్ట్. ఇక్కడ అది ఫోటో ఎలక్ట్రిక్ ఎఫెక్ట్ కాదు ఇక్కడ జరిగేది. ఎలక్ట్రాన్ బయటకు వస్తే ఉపయోగమే ఉంది. ఎలక్ట్రాన్ వ్యాలెన్సీలో ఉండేది కండక్షన్ బ్యాండ్లోకి వస్తే చాలు మనకి సెమీ కండక్టర్స్. It will leave a hole in valency band and a free electron in conduction band. Suddenly, conductivity increases, exposure to the light. So, more is the intensity of light, more high is the change in the current. That you can see in the graph here. You are operating in the reverse biased mode. Right. Now see, at an intensity I1, at an intensity I2, at intensity I3, at intensity I4, you can see the magnitude of the saturation values increases with intensity. You can see that. You can see that here. Can you notice that here? Voice. You can see saturation current, saturation, saturation, saturation. Reverse bias current. So which means the saturation, according to intensity, saturation current is increasing. This helps in comparing intensities of light. So that is the major utility with a photodiode. Okay. Then why? What is the reason behind this? Okay, you are exposing light, fine. So what? The moment you expose the light, the moment when electron hole pairs are created before they recombine, the strength of the field is so high that it makes it to drift or it makes to cross the barrier. I repeat, because of the strong strength of the depletion region electric field, the moment electron hole pair created, before they recombine, electrons are sent to N region, holes are sent to the P region by this field. This adds additional current. Right. Then, ఇక్కడ అది వేరు ఇది వేరు. అసలు ఫోటో ఎలక్ట్రిక్ ఎఫెక్ట్ లో ఎలక్ట్రాన్ కంప్లీట్లీ కమ్ అవుట్. Here it is not coming out, it is just freeing from valency band state and falling onto the conduction band. Completely different. Depending. More is the intensity, more high is the current. Ashmi, following? Right. Reverse bias. Right. See, the magnitude of the photocurrent depends on the intensity of the incident light. That's shown in the graph. It is easier to observe the change in the current with the change in the light intensity only under reverse biased condition. There is a question related to this. This is a very standard question. Lot of times, most of the organizations, they will use this current in their grants. Theory type. The current in the forward bias is known to be more than the current in the reverse bias. What is the reason then to operate the photodiodes in the reverse bias? దీనికి నేను తరచూ పిల్లలకు ఒక ఎగ్జాంపుల్ చెప్తాను. మీరు ఎగ్జాంపుల్ ఫస్ట్ విని తర్వాత క్వశ్చన్లోకి వెళ్దాం. మీరు రోడ్డు మీద వెళ్తూ ఉన్నప్పుడు మన సైడ్ చాలా చోట్ల డ్రైనేజ్ వాటర్ మ్యాన్ హోల్స్ నుంచి బయటకు వస్తూ ఉంటుంది కొద్దిగా కొద్దిగా కొద్దిగా. మీరు సమ్మర్ సీజన్ డ్రైగా ఉన్నప్పుడు ఈ వాటర్ కంపల్సరిగా ఆ మ్యాన్ హోల్ నుంచే వస్తుందని ఐడెంటిఫై చేస్తారు. పిచ్చి వాన పడుతుంది, హెవీ రైన్, ఫ్లడ్లా ఉంది రోడ్డు మీద వాటర్. అప్పుడు కెన్ యూ డిస్టింగ్విష్ బిట్వీన్ ద వాటర్ దట్ కమ్స్ అవుట్ ఆఫ్ ద మ్యాన్ హోల్ and the rainwater? Practically not possible. My answer is same in this question. Reverse biased mode, the current is very small, microamps. Under such small currents, big variations are noticeable. Due to exposure of the light, what maximum will happen? Suppose if the normal conditions, the saturation current is 10 microamps. Because of exposing to the light, it may become 20 microamps. Remember, 10 microampere become 20 microamps because of the exposure of light. So the additional difference is 10 microamps because of exposing to the light, which you can notice. If I am running the system in forward bias, current itself is of the order of milliamps, 2 milliamps. Okay, higher. The change will be 2.001 milliamps, which our instrument may not even detect, or we are not in a state to identify whether it is due to that or not. So that is the reason why we are using this in the reverse biased mode. Why photodiode is used in the reverse biased mode? It is because of this reason only. Okay, so I have discussed successfully the photodiode. The photodiode we will use for what you call majority of the operation is decoding. When you are using optical fibers for communication purpose, for coding and decoding, you require a photodiode. It will convert optical signal to electrical signals, right? Light emitting diode. See, LED is the only one which operates in forward biased mode. LED is heavily doped PN junction diode. బాగా సిగ్నిఫికెన్స్ ఏంటి ఎల్ఈడి సిగ్నిఫికెన్స్? ఎల్ఈడి is heavily doped. This is one of the important significant factors of light emitting diode. See, in this part, what we are doing is we are exposing light to the depletion region. Reverse happens here. When you are using forward biased mode, okay, in the flow, if a hole combine with electron, what happens? Boys, if a hole combines with electron, what happens? Previously, an electron absorbing a photon free from valency band to conduction band, leaving a hole in the valency band. Now speak reverse. If a hole is filled with an electron, then what happens? An equivalent energy of photon is given out. That energy is equal to the energy gap. This is the working principle of light emitting diode. So therefore, in the forward biased mode, when the forward current of the diode is small, okay, what you will notice is a less number of combination takes place. So less intense light will be given out when current is high. But see, there is a two problem here. When the current is very low, intensity is low. As you increase, intensity increases. As you increase further, again, the intensity. Why? Because without recombination itself, the electron will pass nearby the region of the hole. So I repeat, when a forward bias or current of the diode is small, the intensity of the light emitted is small. As the forward current increases, intensity of the light increases and reaches a maximum value. If you further increase, the intensity of the light decreases. So how are LEDs designed? LEDs are designed to have maximum efficiency. Maximum efficiency. Okay, you don't require a separate voltage and current characteristics of an LED. It is as same as a photodiode. I mean, like PN junction diode. It is like, you already know this. That is how you will have a diode. Current, voltage. Same you will have here. Actually, I have drawn forward biased current and voltage characteristics of a PN junction diode. Same you will have. Okay. So what is the additional information that you need to by heart, literally? Like here in inorganic chemistry, how the way you do. See, the first point is you can have LEDs which can emit red, yellow, orange, green, and blue light. You know that. Diwali, you will use all that, right? See, the semiconductors used for fabrication of visible LEDs must have an energy gap at least 1.8 electron volts. At least, right? See, visible light is from 4,000 angstroms to 7,000 angstroms. So 4,000 angstroms corresponds to 3 electron volts, 7,000 angstroms corresponds to 1.8 electron volts. For example, you take one material, semiconductor material, which is called gallium arsenide phosphide. It is represented as GaAs 1 minus x px with fractions of composition. ఎంత పి ఉంది ఎంత ఆర్సనైడ్ ఉందని చెప్తుంది ఆ రిలేషన్. The most of the LEs are used, they are made up of using gallium arsenide phosphide. ఫర్ ఎగ్జాంపుల్ ఈ కాంబినేషన్ మీరు తీసుకుంటే 1.9 ఎలక్ట్రాన్ వోల్ట్ వస్తుంది. సో రెడ్ కలర్ ఎల్ఈడికి ఇది వాడతారు. 1.4 మన రిమోట్స్లో వాడేది ఇది. దిస్ ఈజ్ యూజ్డ్ ఫర్ ఇన్ఫ్రారెడ్. మీరు రిమోట్ ఎక్కడ యూజ్ చేసినా ఈ ఎల్ఈడి ఉన్నట్టే. సార్ మాకు కనిపించదే, పిచ్చి ప్రశ్న అది. అది ఏ రేంజ్లో ఉంటే మీకు కనిపిస్తుంది లైట్? 4,000 యాంగ్స్ట్రామ్స్ టు 7,000 యాంగ్స్ట్రామ్స్లో ఉంటే, 7,000 యాంగ్స్ట్రామ్స్ కన్నా ఎక్కువ ఉంటే మీకు కనిపించదు. నేను ఇక్కడి నుంచి నొక్కితే రిమోట్ కార్ ఆన్ అవుతుంది, మీకు ఎలా కనిపిస్తుంది? ఆర్ మైక్రోవేవ్స్. ఏసీ ఆన్ చేయాలి, యూఆర్ యూజింగ్ రిమోట్. ఇన్ఫ్రారెడ్, దగ్గర ఉండేవి ఇన్ఫ్రారెడ్, రైట్? సో బర్గ్లర్ అలారమ్స్కి యూజ్ చేసేది కూడా ఎల్ఈడినే. ఆప్టికల్ కమ్యూనికేషన్కి యూజ్ చేసేది కూడా ఎల్ఈడినే. ఎల్ఈడీస్ ఆర్ ఎక్స్టెన్సివ్లీ యూజ్డ్ ఇన్ రిమోట్ కంట్రోల్స్, బర్గ్లర్ అలారం సిస్టమ్స్ అండ్ ఆప్టికల్ కమ్యూనికేషన్. ఆల్మోస్ట్, if I am not mistaken, most of the incandescent lamps are nowhere used. Even cars లో కూడా ఎల్ఈడీస్ యూజ్ చేసేస్తున్నారు హెడ్ లైట్స్కి. ఒకప్పుడు హాలోజన్ ల్యాంప్స్ వాడేవాళ్ళు, ఇప్పుడు ఆల్మోస్ట్ అవి కూడా పోయి ఎల్ఈడీస్ వచ్చేసినాయి. నా దానిలో వైట్ ఎల్ఈడీస్, నాకు ఇచ్చింది అది కాదు, హాలోజన్ ల్యాంప్స్ కూడా కాదు, మామూలు ఎల్లో కలర్ లైట్. నేను దానిలో మార్పించుకొని ఐ యూజింగ్ ఎల్ఈడీస్, రైట్? సి, ఎల్ఈడీస్ వల్ల యూజ్ ఏమిటి? ఓవర్ ఇన్కాండిసెంట్ ల్యాంప్స్, లో ఆపరేషనల్ వోల్టేజ్ అండ్ లెస్ పవర్. ఈవెన్ కార్లో యూజ్ చేసేది కూడా నాకు 100 వాట్ అవైలబుల్. నాది 120 వాట్. లాంగ్ బీమ్ 120, షార్ట్ బీమ్ 100 వాట్. 100 వాట్, వెరీ హ్యూజ్ లైట్. అండ్ మామూలుగా అంత మునుపు అంత పవర్ది వాడాలంటే మీరు ఎర్లియర్ డేస్లో స్ట్రీట్ లైట్స్ ఈవినింగ్ 6 ఆన్ చేస్తే ఫుల్ సెట్ లైట్ అరౌండ్ 6:30 కానీ ఆపరేట్ అయ్యేది కాదు. ఏదో ఒక 10 మినిట్స్ అట్లీస్ట్. ఇప్పుడు స్విచ్ ఆన్ చేయగానే ఎల్ఈడి ఆన్ అయిపోతుంది. ఈవెన్ ట్యూబ్ లైట్స్ కూడా చూడండి, స్విచ్ ఆన్ చేయగానే ఎల్ఈడీస్ ఆన్ అయిపోతాయి. బ్యాండ్ విడ్త్ ఆఫ్ ఎమిటెడ్ లైట్ ఈజ్ ఆఫ్ ద రేంజ్ 100 యాంగ్స్ట్రామ్స్ టు 5000 యాంగ్స్ట్రామ్స్. ఆల్మోస్ట్ see, they are available majorly in a monochromatic state also. అంటే ఎక్స్క్లూజివ్ రెడ్, ఎక్స్క్లూజివ్ బ్లూ, ఎక్స్క్లూజివ్ ఎల్లో కావాలంటే దొరుకుతాయి నీకు. లాంగ్ లైఫ్, 3 to 4 years మార్చాల్సిన అవసరమే లేదు. మరి బల్బ్స్ ఇన్కాండిసెంట్ బల్బ్ లోపల ఫిలమెంట్ బేస్డ్ బల్బ్ అయితే పూర్వం 6 months 1 yearకి మార్చాల్సి వచ్చేది. ఫాస్ట్ ఆన్ ఆఫ్ switching capabilities. Next, solar cell. See, solar cell, a solar cell is basically a PN junction which generates EMF when solar radiation falls on the PN junction. You can see here, you have a PN junction here. Can you notice that? See, the surface is exposed to light, whereas the top surface will have a cover. It is like a metal plate, perforated metal plate. Maximum photons it will pass through. And back contact is again a metal plate. What is happening in this case? When you are exposing this light, what will happen is electron hole pair is created like what you have done in photodiode. And for example, the electron hole pair created here, what will happen is because of, across the diode, this is the depletion region. You have P inside, N here. So what will happen when electron hole pair is created? You will have an electric field. Depletion region electric field is like this. So this region drifts electrons up and drifts holes down. These electron which is going up gets collected here. These holes which are going down accumulated here as a positive charge. You may ask me how holes become positive. Practically holes are not becoming positive. To fill these holes, electrons are given out by this conducting plate. Anything that loses electron, attains positive charge. As you keep on exposing light, the charge separation keeps on taking place. As the charge separation keeps on taking place, a potential drop takes place across the topmost metal plate and bottommost metal plate. And this I will use to charge the battery. This is how your solar cell works. See, basically, the IV characteristic curve, very special. It's in 4th quadrant. See, if you use full current, drop will become 0. If you don't use any current, the potential drop is maximum. You will operate somewhere over here. You will operate somewhere over here while you are using that solar power, right? So semiconductor with bandwidth close to 1.5 electron volts are ideal for solar cell fabrications. Solar cells are made up of semiconductor. Like for example, you choose silicon 1.1 electron volts, gallium arsenide 1.43 electron volts. And this is another semiconductor which is close to 1.45 electron volts. Another combination 1.04. See, the important criteria for the selection of the material for solar cell fabrication, one band gap, at least 1 electron volt నుంచి 1 electron volts మధ్యలో ఉండాలి. ఆప్టికల్గా హై అబ్జార్ప్షన్ ఉండాలి. మ్యాక్సిమం లైట్ని అబ్జార్బ్ చేసుకోగలిగేటట్టు ఉండాలి. గుడ్ ఎలక్ట్రికల్ కండక్టివిటీ. ఇంకోటి ఆ మెటీరియల్ అవైలబుల్ కూడా బంగారంలో అవ్వకూడదు. The material is the material which are used for preparing the solar cells, if they are very cost, what is of use? So therefore, solar cells are used in power electronic devices, in satellites, space vehicles, and also as power supply to some calculators. Now you are not using that actually. Production of low-cost photovoltaic cells for large-scale solar energy is now the active topic for research. Right. సో సోలార్ సెల్లో ఏమి బయాస్ ఏమి ఉండదు. ఇన్ఫ్యాక్ట్ ఒక రకంగా చెప్పాలంటే అది కూడా రివర్స్ బయాస్. ఇందులో క్వశ్చన్ తరచు ఎన్సీఆర్టీలో అడిగేది ఒకటి ఉంటుంది. వై ఆర్ సిలికాన్ అండ్ గ్యాలియం ఆర్సెనైడ్ ఆర్ ప్రిఫర్డ్ మెటీరియల్ ఫర్ సోలార్ సెల్. మీరు సోలార్ రేడియేషన్ కనుక చూసుకున్నట్లయితే ఎక్కువ ఫోటాన్స్ రేంజ్ మీరు చూడండి ఒకసారి. మీరు పీక్కి దగ్గరలో this is between 1 electron volt to 1.8 electron volt energy ఉన్నవి ఎక్కువ ఉంటాయి. What the solar radiation we are receiving, in that more number of photons falls in this range. 1 electron, ఇందాక అదే కదా నేను చెప్పింది, 1 electron volt to 1.5 electron, 1.5 దగ్గర ఇంకా పీక్. సో దట్ ఈస్ ద రీజన్ వై గ్యాలియం ఆర్సెనైడ్ బాగా ప్రిఫర్ చేస్తాం మనం. We will use gallium arsenide because of that reason only. Majority of the designing of semiconductor diodes, semiconductor sheets, అదే మనం solar cells, sorry, should correct it as solar cells. Okay na? Right.